Y15 alternating current and RLC circuit. So we first consider LC oscillator. We learn that if a current I flows, if you cross an inductor, the potential changes like that. It is due to the Faraday's law, where the magnetic flux is inductance multiplied by current. And magnetic flux time derivative, we assume that the geometry of the circuit is invariant. And we have Lenz's law, put the negative sign on it. So this is the EMF due to the change in magnetic field passing through a circuit. Because of this, we have a shift in potential along the direction of current. This is like that. If current flows in, positive charge is accumulated on this plate and negatively charged particles are accumulated on here. Therefore, if you cross a capacitor, we have a change in the potential in negative sense, Q over C. And if we return to the same point, suppose that we have a point A, we had a potential VA, and we return to the same potential. And VA cancels. The resultant equation of motion for the circuit is this form. If we divide this equation with the L inductance, we arrive at the same equation as the simple harmonic oscillator. Here, the characteristic frequency omega 0 is just 1/square root of LC. We remember the simple harmonic oscillator keeps its total mechanical energy invariant. Just like that, if we multiply the velocity, velocity is time derivative of displacement. In here, we have no displacement. Instead, x is replaced with the charge q. So what is the time derivative of charge? This is current. If we multiply this current, both sides, right-hand side still vanishing, left-hand side becomes the total time derivative of something that is Hamiltonian, the total mechanical energy in the case of a simple harmonic oscillator. In here, what we have is 1/2 Q dot is I squared, and 1/2 omega 0 is LC. So why don't we multiply L both sides, becomes L, and we have Q squared. This is what? Total electromagnetic field energy. This is the magnetic field energy saved inside the solenoid, the inductor. This is nothing but 1/2 mu 0 magnetic field squared integrated over space. This is what? This is electric field energy density integrated over space. So this is magnetic field energy and this is electric field energy. Sum of this, so electromagnetic field energy saved inside an inductor and capacitor is invariant. It is a constant of motion. Some of this electromagnetic field energy is invariant. If the sum of these two contributions is a constant, and each part is oscillating as a sinusoidal wave, what we have done with the simple harmonic oscillator becomes a carbon copy. Total mechanical energy of the simple harmonic oscillator corresponds to the total electromagnetic field energy saved inside the inductor and the capacitor. What is the frequency? Angular frequency of the motion in the simple harmonic oscillator is square root k over m. Instead, in here, we have 1 over square root of LC. That's the difference. So inductance behaves like the mass of the simple harmonic oscillator. 1 over capacitance behaves like the spring constant in a simple harmonic oscillator. The period of this oscillation can be determined from this fundamental relation that is identical to these two cases, except that the explicit value for omega 0 depends on the system. Why don't we consider the case when a resistor is attached? If the resistor is absent, then the total electromagnetic field energy is completely conserved. However, because this guy loses some energy as a heat, joule heat, because of that, unless there is another power supply, the total electromagnetic field energy decays exponentially due to the resistance. Its mechanical analogy is the damped harmonic oscillator with the x double dot gamma x dot plus omega 0 squared x equals 0. You remember this homogeneous equation. Why don't we move this guy, after replacing this one with the charge, move this one to the right-hand side. Then still the left-hand side, after multiplying by Q dot, that is current I, what we have on the right side is, it used to be Ri multiplied by I, left-hand side this way. What's that? This is the total electromagnetic field energy saved inside the inductor and capacitor. Its time derivative is a real number, positive real number. Resistance is always a positive definite. And current can flow right or left to the left. So in either case, square of a real number is a positive definite. Therefore, minus Ri squared is always negative. What's that? Total electromagnetic field energy decreases the energy is attenuated. As a result, this attenuation factor is exponential minus 1/2 gamma t, where gamma is determined by the resistance over the inductance. If the resistance is very large, then gamma increases. The exponential decay effect for small gamma, large gamma. As R increases, exponential decay factor, this attenuation factor, becomes very, very strong. And the solution for this homogeneous equation, homogeneous means that there is no external power supply. In that case, we have still oscillating factor. That's the reason why this brown curve represents the case where R equals 0. If we increase R, the oscillation decays, amplitude becomes smaller and smaller. And as t goes to infinity, this effect vanishes completely. You can see this oscillation along if we consider the times, we can find the shift of the peak relative to the original peak. It is slightly moving forward. That means this time necessary to return to the same point becomes longer than the simple harmonic oscillator. That means the frequency becomes smaller than the original characteristic frequency. Frequency becomes smaller, and the period becomes a little bit larger than the original case. You will find this is a three-dimensional plot. We have a time. As time goes by, charge saved inside the capacitor. It used to be very large amount, but it decays. This axis represents gamma over 2 omega 0. When gamma becomes 0, what's that? It is simple harmonic oscillation. The amplitude is flat. The amplitude does not decay. However, if we increase gamma, that means R over L increases. It decays exponentially. Overdamped case, if R is large enough, then there is no oscillation anymore. Therefore, the final current and the charge saved inside the capacitor is not oscillating anymore. And the gamma prime is a little bit slightly smaller than original gamma, that is R over L. In between the overdamped case and the underdamped case, we have a critically damped case. In that case, still attenuation factor exists, but it is not oscillating anymore. However, we have two pieces multiplied to this attenuation exponential decaying factor. It is a linear function. In case beta is not equal to 0, we have an exponential function multiplied by a linear function. The resultant function has a bump, just like this. However, it is not general. If beta equals 0, it is strictly decreasing. Anyway, this is a special feature of the critically damped case. Next, we consider the alternating current. Sorry about that. Because of the damping, we need to supply additional power. There is no way to avoid the resistance absolutely, except that you reach the absolute temperature 0. So there are two cases. You attach a battery that gives a direct current. Direct current is a direction of current I is fixed. Your battery is a positive and negative terminal. Current I flows out always, and current I flows in this way. Alternating current you can make use of Faraday's law to generate the electricity. In that case, in general, you will obtain alternating current. This is most of generators uses this way. So that's the reason why we are using mostly using alternating current instead of direct current. In Korea, we have 60 hertz frequency. In Europe, they have 50 hertz. So this is not general. It depends on countries. And if you travel abroad, many countries have different shape of plugs and voltages. So you should be careful. Anyway, the abbreviation for alternating current is AC. The direct current is DC. We make use of Faraday's law to produce alternating current. Driven RLC circuit. Now we attach a power supply that is driven with the driving frequency omega. I have written this power supply's EMF with the amplitude E0, that is a real number, constant, the cosine, sine, or exponential. In any case, we will arrive at the same style of the result. The most convenient way is to make use of exponential one. The reason is that exponential function produce a consistent factor if you take the derivative or if you integrate simple factor. However, if you take the derivative of sine, it has cosine. Unfortunately, it's the derivative of cosine negative sine. complicated. Integral, again, its shape is different from its own shape because derivative and integration will bring in the phase shift. Phase shift. You know, sine function and cosine function, their shapes are the same, but they are identical to each other after some translation by half a pi. This is the phase difference between sine and cosine. However, if we deal with exponential function by attaching I, then derivative will bring in factor of I in the numerator or denominator, and this I is always expressed in terms of half of pi I minus I, that is 1 over I, that is 1 over half of pi I, that is e to the minus half of pi I. So to deal with the phase difference, exponential function is a much simpler than dealing with sine or cosine. However, in any case, your result must be the same. Anyway, if there is no power supply, the output EMF or output current must decay as time goes by. However, because of the power supply, you don't find any complete decay of amplitude. Instead, at t is relatively small, you have a very big shift from these are called the steady state. So they are uniform as t goes to infinity. This means these are steady states and these are transient effect. It passes away as t goes by. Those are originated from the solution of a homogeneous equation. So from now on, we are interested in the steady state solution, neglecting the solution coming from the homogeneous equation. Your circuit equation for general RLC circuit is of this form. You learned this one already in the last semester, and a few weeks ago we reviewed the driven damped harmonic oscillator already, so I don't want to repeat, so you can review. Anyway, the driving force can be expressed as a sinusoidal function. One can make use of cosine, sine, or exponential in any case. You will find, and what we already have found, that there is a phase shift delta. This is a particular solution that reproduces the right-hand side. I'm not interested in the solution for the homogeneous equation. I'm interested in reproducing the right-hand side by substituting some trial solution with the same frequency as the not equal to the omega 0, but equal to this driving frequency. We assume there is a phase shift. Whether you use cosine, sine, or exponential, these phase shifts are exactly the same, always. This delta must be there because we have this term. This and this doesn't care because you take the derivative twice, cosine becomes cosine, sine becomes a sine, exponential becomes exponential, the same function. But only the resistive factor, resistive term will flip cosine into sine and sine cosine. It becomes 30. Anyway, because of that, there must be a phase shift delta. And that delta is completely determined by substituting this one to the left-hand side, comparing both sides, you have a condition. And this condition is identical to any case for sine omega t input, cosine omega t input, or exponential I omega t input. In any case, we have the same phase shift. And this phase shift is completely determined by the characteristic frequency, driving frequency, and R over L. And omega 0 squared is 1 over LC. So if you know R, L, and C, you can determine this phase shift of the phase completely. Okay. And this one is a sine and this one is cosine. So square sine square delta plus cosine square delta, it must be 1. So this guy, this guy, this guy, this guy, they are the same. So whatever omega, whatever gamma, omega 0, omega, whatever value you substitute, these two numbers are cosine and sine, and their square sum must be unity. You know, there is a denominator. This denominator is a function of omega, and that determines the amplitude, resultant amplitude of the output. And you will find at some omega, spatial value omega, this amplitude is maximized. That is called resonance. If you have gamma, that is R over L, is very large, this peak becomes broader and broader, and R goes to infinity, it is just a flat. When R is a 0, it becomes a very, very sharp peak to the infinity. So condition of a resonance is just the derivative of this amplitude, which is a function of omega, should be 0. So in the case of current, this is the amplitude for the charge Q that corresponds to the displacement in the simple harmonic oscillator. But if we consider a circuit, we are more interested in the current rather than the charge saved inside the capacitor. So current is equivalent to the velocity in a simple harmonic oscillator. The resonance of the amplitude A and the resonance of the amplitude A for the current are different. Resonance appears in here slightly smaller than the characteristic frequency if we consider Q, but if you consider the amplitude for the current, we have additional factor omega in the numerator. In that case, the exact value of omega 0 is the same as the resonance frequency. So this is a slightly different from the analysis for the displacement, the velocity of the simple harmonic oscillator corresponds to the current in the circuit, and we have a very trivial relation for the resonance frequency.